Hey everybody, my name is Jeffrey Gillan and welcome to NextGen Geospatial, the U of A Data Science Workshop Series, where we are doing all kinds of unique things in geospatial, focusing on open geospatial, cloud native geospatial, stuff you just typically don't learn in most GIS or remote sensing classes that are taught here at the University of Arizona. By no fault of the teacher's own, this is just the stuff we're hitting here is a bit more cutting edge. And yeah, it's kind of we're just trying to hit the cutting edge stuff. So today's session, let me share my screen here. So for today's session, we have an hour to talk about cloud optimized point clouds. So we're continuing with our cloud native theme. The last two sessions, previous 2 weeks, we talked about cloud native, and it's the concept that we can do full geospatial workflows in the cloud without having to actually download data to your machine. And there's several advantages to that. I'm not going to recap all of that. You can go back to previous lessons and kind of see the the why of all this, and why would we want to do stuff in the cloud. So today let's focus on cloud optimized point clouds.
Sure, no problem.
Okay, go ahead, Carlos. And let me put this material in the chat, just in case some of you have recently joined. So I'm putting today's course content in the chat, and you can follow along if you want, or you can just watch my screen. You don't have to actually go to the content if you don't want to. So what are geospatial point clouds? I don't know. I imagine a lot of people do not work with them directly. So what are they? They are a 3D representation of the world. And typically they would be created through photogrammetry means or through LiDAR. So photogrammetry means is you fly a drone or you fly an aircraft or something, and you're collecting imagery, just two-dimensional, photos, but you're collecting them in a overlapping fashion, meaning the same point on the ground is being photographed from multiple angles. And through the magic of aerial triangulation and some really fancy software, we can build three-dimensional models from it. And we'll see some examples of that here in a little bit. Additionally, point clouds can be made from LiDAR, which is light detection and ranging. You can also call it laser scanning. It's very similar to radar, only we're generally using light from the near infrared spectrum. We shoot a beam of light. It goes at the speed of light, hits an object like a tree or the ground, bounces back up to our sensor, and we know the speed of light. And so all we have to do is record how much time it took for that light to hit the surface and come back. If we do that millions and hundreds of millions of times, we can make a three-dimensional map of return times for light pulses. And so you can make very dense and very amazingly accurate three-dimensional models of the landscape. So I would kind of put geospatial point clouds in I'd call them vector, because every point has an X, Y, and Z coordinate. It's not a raster, but it's a special type of vector. And we usually store them in something called a LAS format. So that's kind of the standard format that everyone in remote sensing uses for LiDAR and photogrammetry point clouds. And just like other formats, they can be viewed in many GIS remote sensing type software packages. Cloud Compare is one of my favorites. It's an open source one. So it's you can just download it for free. It is probably the best visualization you can do for point clouds. And then other GISs like QGIS and ArcGIS have no problem of bringing point cloud data in to then view and analyze it. So up on the screen, just have a few examples of point clouds. These are all photogrammetric point clouds. So these are all made by me flying a drone, and I flew the drone, collected hundreds to thousands of images of, whatever 5-10 acre piece of land that I was photographing. And so a lot of these images are overlapping. It means we're we're hitting the same piece of ground, multiple times from multiple perspectives. And with the properties of triangles, we can make three-dimensional maps with it. So up here we have a forest. This is from the top of Mount Lemmon, just outside of Tucson. This is a scene in the Chihuahuan Desert outside Las Cruces, New Mexico. And this is a scene in the Santa Rita Experimental Range, just south of Tucson. So that's a shrub and some grass. And so you can get, depending on how low you fly the aircraft, you can get very, very high resolution three-dimensional models. And from those models, you can measure all kinds of things. Yeah, I see a raised hand. Go ahead.
Jeff, I
Yeah.
have two questions. My first question is the resolution that you get from like LiDAR versus drones. What are their resolutions? Like I saw like it's sub-meter with the LiDAR. What resolutions do you get from drones?
Um, from drones, so from photogrammetry and from LiDAR, the resolution can be really depends on how close you are to your target. If I fly the drone 10 feet above the ground, my resolution is going to be sub-millimeter, probably. Same with LiDAR. It's all about how close are you to your subject. So if you've said that you've seen LiDAR that's sub-meter, that's probably from an airplane, and they're flying, maybe a couple thousand feet above the ground. And yeah, typically from an airplane, they're getting like 3, 4, 5 points per meter. Maybe better than that, but if you flew the aircraft a lot lower, i.e., the sensor a lot lower, you could get hundreds of points per square meter. So it just really depends on how
Okay.
close you are to your subject.
Okay,
It could be anything.
I have
Sure.
one more question, and that's a request too. Um, when I used the Cloud Compare in the past, it crashed many times. Um, so is it possible if you could show us how to use Point Cloud in QGIS? Like you showed like georeference TIFF files, um, COGS. So if you could show us how do you do this in the QGIS, I'll really appreciate that.
Okay, well, it's actually covered in my content here. If you would scroll
Okay.
down in the content, there's actually like, here's how you do it in QGIS. We're not going to go through it together because I want to spend time on other things, but um, in terms of visualization, I'm sorry Cloud Compare has crashed on you. That's kind of a strange issue. I've never had that issue before. Um, but to me, Cloud Compare, in my experience, has always been like a superior way to visualize point cloud data. And QGIS, not so great. QGIS is, I think, better for analysis, and there's a lot of different tools. But in terms of just looking at a point cloud and yeah, with the naked eye and just kind of panning around the scene, nothing beats Cloud Compare. Okay, well, let's keep rolling. Thank you for the questions, though. So point clouds are I would say a special type of vector geospatial data. It's being used, to 3D model the land and any kind of object on top of the land for all kinds of purposes. LiDAR is being used. That's how self-driving cars can see the world, so to speak, is they have lasers going real time, and so they can see something in front of it and then react to it. In my world, natural resources, we're using it for forestry big time. We could fly over a forest and identify every single tree and quantify um, total biomass, total green biomass, how many estimated board feet, um, quantify wildlife habitat. I mean, it is just an amazing technology to be able to sense in very detailed 3 dimensions the landscape and be able to then bring it into your computer environment and then analyze it and measure and manipulate in ways you couldn't possibly do, on the ground or in the real world. So let's talk about cloud optimized point clouds. So cloud optimize, this was developed by a company called Hobu, which is short for the leader of that group is Howard Butler. And so a cloud optimized point cloud, you could call it a COPSI. Let's call it a COPSI for short. It is similar in concept to the COG or the Cloud Optimized GeoTIFF. So a COPSI is just an LAZ format, which is an LAS zip. So this is a standard format that all, LiDAR or photogrammetric point clouds use. The difference is it's organized a little bit different, and it uses something called octree organization. We're not going to go into what that means. It's kind of hard to explain. But anyway, it does the same thing or a similar thing to what the cog uses for overviews and tiles. And so with a COPSI, you can stream a portion of, like a big point cloud. You can stream it from cloud storage across the internet to any application, and you don't have to download the whole thing. And so when you're visualizing it, which we'll see just here in a little bit, same thing. As I'm doing a visualization in an app, in an app or something, I don't have to get all of the data all at once. It's more like as you zoom in and out of the point cloud, you can see it starting to render more detailed or less detailed, depending on how close you are to the ground or the bottom of the image. So that's what a COPSI or cloud optimized point cloud is. It's just a point cloud, but it's been rearranged to more easily stream across the internet to then be worked with directly in the cloud, and don't necessarily have to download giant gigabyte files to your local machine to do analysis. All right, let's look at some examples of the cloud optimized point cloud. So I have a few that are sitting in the Cyverse data store, which is, object cloud storage here at the University of Arizona. And I'll just click on this viewer here. Okay, so this is a photogrammetric point cloud that I collected and created. This is Paradise Valley Country Club up in Phoenix. And so this data is sitting in on a server, the Cyverse data store, and it's being streamed to another server where this web app exists, viewer.copc.io. So yeah, we've got a few different things going on here. It's data is being streamed from cloud storage to another server, which is hosting this website, which is created a nice visualization of it, and then I'm tapping into that server to then be able to see this in my browser. And so let me just kind of zoom in here. And as you see, as I zoom in, it gets more resolute. You can see the tiles starting to kind of form. Yeah. So that's kind of the octree organization in action there. Yeah, so this is just a nice visualization of a golf course. We have the trees, we have the fairway. And so I collected and processed this imagery for the country club because they're interested in installing irrigation line, subsurface drip irrigation throughout this entire fairway. And so they wanted a really detailed three-dimensional survey or, topographic map so they knew how to best install the irrigation line. Look at some of the houses here. So we have some nice properties that are right by the golf course. So yeah, it just kind of gives you an idea of the kind of detail, three-dimensional modeling you can do with a pretty inexpensive drone and just with like a regular camera. It's just a two-dimensional camera, nothing fancy. But you take hundreds or even thousands of photos and you do some really fancy software processing, doing something called aerial triangulation, and you can make some really cool looking three-dimensional maps. Okay, let's keep on rolling. Let's look at another example of another cloud optimized point cloud. This is LiDAR. So this was from an airplane that flew over Prescott, Arizona, and made a three-dimensional map. So if you've ever been to Prescott, I'm zooming in on the casino that's up at the top of a hill, in the middle of Prescott. That's what this is here. So it's not nearly as detailed. It's coarser because this is from a airplane, and so the data is further, or the subject is further away from the sensor, and we don't get as like detailed or resolute type data as you can get from a low flow flying drone. But nonetheless, it's super useful data. You could use this for all kinds of purposes regarding civil infrastructure, forestry, building management, building permits. I mean, the list is kind of endless. It's just a very nice three-dimensional model for which you can do all kinds of different mapping applications. Let's see, we can change things. So in my menu over here, I can change the visualization. Currently, it's showing elevation. If I did intensity, what does that do? Okay, so things have changed a little bit. And so now I'm looking at the intensity of the laser returns. And so you can kind of think about this as kind of like reflectance, like in a passive sensor. It's not quite like that, but it's similar. The light from our sensor goes down to the ground, hits the object, and then comes back. And depending on what that object is, will dictate how much of that light is absorbed or reflected. And so things that are like very reflective, like a white roof on top of a house or something is very reflective. And so that's probably going to have a whiter or a higher reflectance signal.
That's the albedo.
Yeah, right. Albedo. The parking lot, which is asphalt, is black and it's going to have a lower one. So the light hits it and it absorbs more light than it probably reflects.
The USGS project for the 3D, it's a 12-inch resolution or 30 centimeters resolution.
Okay, so they've taken LiDAR and they've made digital elevation models at, what do you say it was?
30 centimeters.
30 centimeters. Okay. Which is about a foot.
Yeah,
Yeah.
12 inches.
Right. Okay, thank you for bringing that up, Carlos. We're actually gonna look at 3dep. And I got a question here. Let's see, Garrett, do you have a brand model of drone that you would recommend? That is a a much longer conversation, and can't hit it here. You can hit me up afterward. We could talk about it. That's not a cut and dry situation. Oh yeah, I'm gonna have to go back to my. Okay. Okay, so you've seen a few cloud optimized point clouds. We can visualize it. We can stream it from storage somewhere into an application. Here are the instructions of how you would do this in QGIS. So it's pretty simple. It's just like how you add data, only you're adding data from an HTTP address. And so, yeah, here's just some instructions you can follow if you would like to do that on your own time in QGIS. Yeah, but keep in mind, like, I don't think the visualization is that fantastic. It does visualize in 3D, but I prefer other programs. Okay, how do you create your own cloud optimized point cloud? Well, we have to use a software program called PDAL, which is a point data abstraction library. And so that is kind of a cousin to GDAL. It's kind of made in its image, but this is specifically for point cloud data. Again, we're not gonna go into all the details of how to do this in PDAL. It's kind of a slog. It's really not that like super interesting, but I have instructions on how to do it. PDAL is a command line tool, so it is not it's not graphical user based. You're not going to point and click with the mouse. You are going to install it and then you're going to access it through your command line and give it commands like this, and like this. It's fairly easy to do, but yeah, some familiarity with typing commands on a command prompt could help. So it's not too hard to make, if you follow the instructions. Okay, it's 221. Let's talk about entwine point tiles. So entwine point tiles, are EPT, is another cloud optimized format, and it is very similar functionally to a COPC, but it's like the previous generation. So the idea for how to stream point clouds across the web really came into its own with this EPT, or entwine point tile. But the kind of limitation is it consists of like thousands of small little files that are organized in a directory structure. So practically speaking, it was just kind of annoying to move them around, and they consisted of all of these little JSON files. And so Howard Butler and his group took the same idea, and let's like package it into something that's just simpler and more discrete, but does the same cool thing. And so that's how the cloud optimized point cloud came to be. So cloud optimized point clouds this is still cutting edge thing. There isn't mass adoption out there. People are using LAS everywhere, but this cloud optimized concept around point clouds is not very old. Really in the last couple years. And so you're not going to go out and find a huge amount of these that exist already. The one kind of thing that you can find in terms of existing data is from the US Geological Survey. And so they have a program called the 3DEP program, or the 3D elevation program. And so basically they have three-dimensional topography data, or digital elevation models, for almost the entire country. And they are kind of ahead of the curve in terms of this cloud native technology. And they have a huge amount of LiDAR across the country in this entwine point tile format that you can just grab and use. Let me go here. Let's look at what they have. And so here's the United States. And so this is them showing us where they have LiDAR in a entwine point tile format. And they have it, about everywhere. They don't have it in the middle of Nevada, and it's kind of sparse in Navajo country. But a lot of other places they have. Let's see here. If you go look at Tucson, which is right here, we have total coverage around Tucson and Mount Lemmon, and most places really. Okay. So EPT, very similar to a COPC, cloud native point cloud format. So that's what we're going to do in our hands-on activity is we're going to generate and visualize digital elevation models using 3DEP data from the USGS. So this is LiDAR data, and we're going to do this in a cloud native fashion. So we're going to do this in a Jupyter notebook hosted on Google Colab. If you remember, a Jupyter notebook is just like a software environment, a place to write code and run code that you access through your browser. And we're going to open it in Google's Colaboratory, or Google Colab. And that just means we start an instance of it on a Google computer, and we tap into it. And so all the processing that we'll be doing will be done on a virtual computer, but not my own laptop. My laptop is a window into what we're doing. Yeah, okay, let's just open the Colab. So open link in new tab. Okay, so this should be unique to everyone, basically. Sign in. What does it have me signed in as? Let's go ahead and sign in through my U of A account. This thing is super annoying. Okay, so I did not write this Jupyter notebook. It was written by people from Open Topography and the San Diego Supercomputing Center. So these are the authors that actually did this. And hats off to them. What we're about to do is pretty amazing and a bit complex. We do have a hand raise, so go ahead with your question.
Jeff, can you please go a little bit slow when explaining the code portion? Just a request.
Today is not the day to do that. I'm sorry. I can explain what kind of the code is doing, but is really outside the scope of this hour workshop to explain in detail. That really is something that you're going to have to just kind of look at yourself, play with, and figure out. And yeah, we can't possibly go through every line, and this is what this line is doing in this short workshop. Just can't do it. That's another type of workshop, I think. Okay, but the purpose of today is to give you a big picture about what this Jupyter notebook can do, and you have access to it. You know, it's here in the course material. You can click on it anytime. You can save it to your own desktop, your own GitHub account, your own Google Drive account, and change it and play with it and manipulate it for your own purposes. Okay, what we're going to do here is we're going to take LiDAR data from the USGS. And so this is cloud native. This is a entwine point tile format, and it's sitting in cloud storage in a Amazon Web Service or AWS bucket. Okay, so it's sitting in cloud storage on commercial cloud owned by Amazon. So that's where the data is located. And through some really fancy coding, we are going to make an area of interest, basically like a bounding box. And we're going to pull the data from Amazon, and we're going to do some basic analysis. We'll take the LiDAR points and we'll turn them into a digital elevation model or raster, and then do some simple visualization with it. Again, this is the most complex notebook I've ever tried to show. I don't understand everything that was done in this. I know that it works, but all the code, it's kind of beyond me. So there's not really a lot I can explain. But it's great that other people have done good work and we can build on top of it. Okay, we're doing this in Google Colab. I'm going to connect here, connect to my resources. We'll probably have 12 gigabytes of RAM, which should work. 12 gigabytes of RAM, 107 gigabytes total of disk. We're not going to really use much of that. So this first block of code, this is interesting. So to work with PDAL or GDAL in a Jupyter Notebook environment, you can't just use the Python libraries. GDAL and PDAL actually have to be installed on your local machine for it to work. And the Python is simply like another way to access the GDAL and PDAL software. You can call this a binding. I've heard that terminology before. So that's what we're doing. But instead of installing it to like my laptop here, I'm installing it locally to the Google computer that I've tapped into. So on my virtual machine, I am going to install PDAL and GDAL. I didn't know this was actually possible a couple weeks ago, but indeed you can install things on the Google virtual machine, albeit temporarily. Like everything we do in Google Colab, this is going to vanish in a matter of, I don't know how many hours, half of a day or something. This will just poof, disappear forever. So these are great environments, but they are not permanent. All right. So this might take a couple minutes. So to do this, it is demanding access to my Google Drive. And so it's going to stick a few files, I believe, into my Google Drive. And I'll just go ahead and do that. Sure, my university account. Okay, this might take a minute or two. So we are in downloading. What are we doing here? We are downloading a repository from GitHub. That's what this is doing. It's not downloading it to my laptop, it's downloading it to my virtual machine that I'm tapped into. And then it's going to install pdoll and gdoll. And it's going to spit out a whole lot of stuff at me. And chances are it might fail the first time through. That's happened to me the last few times. That said it was going to take a few minutes, take 2 to 3 minutes to do. How long it really takes. Let's see, my RAM is not really doing much. Okay, it's still going. Your session crashed. Okay. Yeah, this happened to me last time. And I'm like, all right, well, let's just try it again. And this time it ought to work. Why? I have no idea.
It did on my system too, Jeff, and when I restarted, it completed the job.
Yep, exactly. I don't understand why. Yeah, I bet this will work now. The first time it doesn't work. This is the third time I've done this, and same result each time. So it should work here in a sec. Yeah, it worked. Why? I don't know. Everything looks okay. Okay. Thank you. Okay, come on, finish. Okay, woo, we finished. Okay, a bit more setup. We're importing libraries, the operating system, the system. That's easy to do. Okay, let's bring in a bunch of different modules. So these are Python libraries. We're going to bring them into our computing environment. Most of these have already been installed. Stock, when you just get into Google Colab, they have a whole bunch of Python libraries already installed. So we're just going to bring them in. Okay. Now they have this ridiculous amount of function defining. And I can't possibly go through all this and explain what everything is doing. I'm just going to hit play. It is defining a whole lot of things regarding projections. Let's see what else. Importing shapefile to Shapely. That's interesting. It's building pdoll pipelines. And so, like I mentioned, pdoll is the tool to make cloud optimized point clouds. It's also the tool to use and if you want to do cloud optimized analysis. So we're going to be doing that. Just skip all this stuff. It might take me months to figure out exactly everything it's doing, but I promise you this works. Okay, now we have to set up our area of interest. Let's see that. Get GeoJSON file for 3-dep outlines from URL. Okay. So what this block of code is doing is going into a GitHub repository and finding the boundaries of all of the EPT files that exist and making a JSON file. out of a GeoJSON file. Thank you. Now, okay, now we can get our interactive map. So this is where I find very fancy when Python code can make these interactive things. It's really quite amazing. And so they give you an option here. You can upload a shape file to define your area of interest, or you can use this interactive way. So we'll do that. And then this code block should actually create this map. Then I can then draw like a square or bounding box of like what part in the country would I actually like to pull data from. Yeah, okay, here it is. So these are all of the polygons that represent all of the LiDAR data that the USGS has in this cloud native format. And you use either this like pentagon or square to make a bounding box. And the thing to really be careful here is not to make it big. If you take a square and be like, I'd like to do half of Texas, it will crash your session, guaranteed. They even have a little warning. Let's read what the warning says. Yeah, it must be too far down. Oh, here's the warning. Yeah, it's in red. Point clouds can get very large very fast. If you do anything over 50 to 100 million points, chances are it will not work in Google Colab. You're going to max out your resources. And so for our purposes, I'm going to do something just super small. Let's zoom into something. Where am I? Tucson. Okay. Elcon Mall in Tucson, Arizona. I bet a lot of us have probably been there, probably have an idea of what it is. So there's my bounding box. Yeah, in terms of all the LiDAR available in the country, I would just like LiDAR just from this little area. Okay, and it said the area of interest is valid. Okay, my little square here. Okay, and based on that square here, it's going to pull what information am I trying to pull out of it. So it already knows that I'm getting LiDAR data from Pima County, and here's the coordinates. And here's where I'm getting it from, Amazon, AWS. So that's where this data is sitting in commercial cloud storage. Okay. What else? Specify point cloud resolution. Let's click that. Guess I don't know what all that one did. Okay, yeah, it did this. It set this up. And so it made another interactive visual here. And so from this, I have to choose what type of resolution I would like the LiDAR to be. So if I get full resolution, that's 11 million points just in that little area of Elcon Mall. That might crash my collabs. And so I'm gonna do mid. I don't know how many points that is, but it should be okay. So all I did is like click the radio button for mid. Okay, so now I know where I want it and what resolution I want it. And now we have to do some PDAL pipelining. And don't worry about exactly what I'm doing. It's too much to really explain. The fact is, I don't really understand it yet. I've only looked at this for the last few weeks. And it is very complex notebook, but the outcome is what I care about. DEMs. Okay, so I can get my LiDAR point clouds. I've got them. So now I can actually create a digital elevation model. So if you don't know what that is or how to do it, so a point cloud is a 3-dimensional vector geospatial file, right? Every point has an X, Y, and a Z. A DEM is a 2-dimensional raster image. Just think of like you're looking in your computer screen, you see an image. That's what a raster is. And it interpolates. It takes the points and interpolates them. It goes from 3D to 2D. And so a DEM, a digital elevation model, is a two-dimensional representation of the surface of the ground. Okay, I've done that. That. Okay, everything's looking successful so far. Let's make my digital terrain model. A digital terrain model is a DEM, but in theory, only the ground. So anything that was on top of the ground, like a building or a tree or something like that, is not included in TTM. And at the end, we're going to do some visualization just to look at the DTM. We're going to use a library called Rio X-Array and matplotlib to do this visualization. Okay, downsample. Wants us to downsample so we can visualize it more efficiently. I'm curious what happens if you don't downsample. Okay, so we finally have our visual to prove that all of this actually worked. So what you're looking at here is a digital terrain model. The colors represent elevation, probably in meters. Yep, right there, digital elevation model in meters. What you're looking at is Elcon Mall area, but the buildings of the mall have been wiped away, and that's what you see in the white. Is just, there's no data there. It's just nothing, no data values. So we've created a digital terrain model with holes for where the buildings should be. Okay, and so that's just like a mapping visual of the LiDAR data that we got and did a little bit of analysis. Then we can also do some kind of descriptive graphics. This is showing a histogram of all the elevation data in our little area of interest. It looks like the average height is somewhere around 765 meters above the ground. Does that sound right in terms of the elevation of Tucson? 2,500 feet? Yeah, I think that's right. Okay, so yes, this is a really complex Jupyter notebook. I don't claim to understand every single line of code that it did, but what it did demonstrate is that there is all of the USGS's LiDAR data is sitting in Amazon Web Services storage, and you can use this Jupyter notebook and tools like PDAL to just tap into it via the internet, grab it, bring it into your Python environment, just a little area of interest that's interest to you, and do any kind of analysis you want. We just did a simple, how do you go from a point cloud to a digital terrain model, and then make a visualization. So just kind of a demonstration of another workflow where you don't actually have to download the data. So the opposite workflow, or the conventional one, would be I go to USGS and I download the entire scene, and that could be for the entire Tucson area or entire Southern Arizona area. I'm not sure how big their LiDAR scenes are. And so this is an alternative. Get what you want, pull it over the internet, bring it into your computing environment, your analysis environment, do the analysis you want, and don't worry about all the other data, coming to your computer that you're not using. And down here is a whole bunch of other examples that were put together by the same folks. So Open Topography is the group. I think they're based out of Arizona State up in Tempe and San Diego State University. And they have seven of these that I think all kind of do similar things, where you can pull in this cloud native point clouds and do all types of kind of topography analysis. all in the cloud. Yeah, it's pretty cool.
That's a question.
Sure. Let's see, look in the chat here. How do you download the final product to your system, Jeff? That's a good question.
But you can file save Jupyter Notebook to your local.
Yeah, do you mean the final product as in the terrain model or the notebook?
A terrain model.
Terrain model. Okay. I don't know off the top of my head. So in the first notebook that I did on geospatial APIs, I have that line of code in there where you can pull it directly and just like download it, I feel. Yeah, from Google Colab onto your actual laptop. Do we have it here? I think
If it's
so.
an image, you can just mouse control click save the image to your computer. If
You
it's
mean
an
like
image, that one.
this one
You
here?
just control.
Yeah, I don't think that's what he means. He wants to get like the actual, this would just be like a PNG or something.
Yeah, I wanted like a TIFF file so that I can process it in QGIS for the
Right.
analysis.
Okay. No, off the top of my head, I don't think I know exactly. It's all doable. Yeah, I just don't know exactly how to do that at this moment. I would ask GPT-4 how to do it.
Well, you can download the Jupyter Notebook to your computer, and if it's powerful enough, it will run. It will do the
Right,
same
okay,
as Google
right.
Colab.
Yeah, as Carlos is saying, you don't have to use Google Colab. You could just run this Jupyter Notebook on your own local machine, and then everything is coming to your local machine. We're using Google Colab because it's a great teaching tool. Help people learn how to do stuff, but it is kind of limited in terms of resources. So yeah, you could just do it to your local machine. Run a Jupyter Notebook on your local.
Okay, thank you.
And also, depending what Python environment you have installed in your computer, like if you're using Anaconda Python, then probably you need to install all the required libraries because your local environment will be different than the Google Colab environment. So just
Absolutely.
install whatever library is missing from the place.
Yes, I like to work on the cloud because I find setting up environments on my local machine is such a hassle that I just avoid it, honestly. For this one, you'd have to, download and install lots of different Python libraries and install GDAL and PDAL on your local machine. You're gonna find a lot of I don't know, ways to trip you up doing that. And I find working on a virtual machine or in the cloud just simplifies things so much. So that's a big motivation of why I do things in the cloud. It's just easier than trying to install things on your local machine a lot of times. Okay, so it's 2:50. I'm done with the content.